Okay, welcome back to a new physics tutorial. In this video I would like to talk about differential calculus. Yeah, this is a very fundamental topic, but I think if you want to do physics, yeah, it's not possible to do it without knowing how this differential calculus works. So what I want to do in this video, I want to explain the fundamental basics. I want to show graphically why this method works, how it works, derive the differential quotient, explain how you can calculate the slope of a function at a certain point, and also do this on the with the help of an example. And I will explain another method how to write down this differential quotient with the so-called H method, because both appear from time to time in several textbooks, and I think it's good to be familiar with both of these methods. So before we go into the details, I would again like to draw a coordinate system here and then explain graphically what we want to do. So of course we can draw any function that ever we want. Maybe this could be a square root of x or a logarithm of x. It doesn't matter so much. The most important thing is that that you can see the slope changes along the graph. So the slope of the function here at this point, of course, is completely different from here. And the main idea behind differential calculus is to calculate the slope of a function at any point, any arbitrary point of this function. So in order to do that, we first define one point here, which is called P1. And of course, this point P1, maybe we can use another color for that, must have a certain x position, maybe we call it x1, and also a function value, which is of course y of x1. And if we want to calculate the slope here, then we don't have to do this analytically. We can also do this graphically, actually. So what we can do, we can draw, maybe you can use another color for that. We can draw a tangent to this function at this point P1. I will try to make it as good as possible. And then we can calculate the slope of this tangent very easily by just drawing here this triangle, delta x, delta y. And then, of course, if we want to write here the slope of this tangent, then we can write down m equal delta y over delta x. So we can just use two x values, x1, x2, two y values, y1, y2 at these certain x positions, and then you can just calculate the slope with the help of this difference quotient. Okay, so this is actually easy, but however, in some cases you cannot use this graphical method, or in some cases you don't want to do it because you want to get an analytic solution. So what we have to do then in the next step, we have to use differential calculus. Without differential calculus, it's not possible to do that. And this is also the main motivation behind that, why it has been invented. So what to do is that we define another point here, P2, and then we can draw a second through that. And maybe I can use purple for that. So first of all, I would like to draw a connection between these 2 points. And then I will extend this here to make it visible. So now we have a second through these points, not a tangent anymore, but a line which intersects this graph at 2 positions. And we could also calculate the slope of that easily. This we can also write down. So of course we have here also, sorry, I will use the same color which we have used before. So we have here our position x2, and of course we have also here our y value, the function value y of x2, and then we can calculate the slope of this second according to m equal, and then what we have to do, similar to what we have done for the second, what we have done for the tangent here, is actually to write down y of x2 minus y of x1 divided by x2 minus x1. Yeah, so we just used, we can just draw this triangle here, which we have drawn here, and then we can calculate the slope according to that. However, we are not interested in the slope of that. We want to have the slope at the position x1. So the idea behind differential calculus is now that we shift this point P1 close to this point P2 close to P1, and as soon as both points are placed at the same position x1 here, then this second turns into a tangent, and then we have the slope of this tangent at P1. So it sounds of course very easy. We have to just shift P1 to P2 to P1, but unfortunately, of course, the main difficulty lies then in the calculation. Yeah. So the problem is when P2 shifts to P1, x2 has to shift to x1. Yeah. And the problem is that here you can see immediately in this formula, if you set x1 equal to x2, this difference would become 0. Yeah? And you cannot divide any function by or any value by 0. This means that this quotient, as we have written down here, cannot work. Yeah? So it for the purpose for which we need it, it cannot be calculated according to that. It's very similar how we will do it, but not exactly according to that. So what we have to do, we have to convert this into the so-called differential quotient. Yeah, so this was the quotient of differences, and now we have to make a differential quotient from that, which means we have to use the limit, the mathematical limit, which can be applied on any function. So how we do that, we write here m, which is then a function now, limit, and then we write here x2 tends to x1. It could be also the other way around. We could say x1 tends to x2. It doesn't matter, because at the end the only important thing is that one point tends to the other. So then we can write here y of x2 minus y of x1 divided by x2 minus x1. Okay, so you can see in principle it looks exactly how we have written it down before. The only difference is that now we have inserted this limit in front, and yeah, then it gets actually, or basically then it's done. We don't have to do anything further. This is already our derivative of y. Yeah, we can write it here, y prime. This illustrates that we are now working with a derivative of y prime with respect to x at the position x1, because we shift x2 to x1. So now we calculated the derivative, as I said, with respect to x, but at the position x1. So, and if you understand that concept, then you have understood everything which is important for differential calculus. And now you would be able, with the help of this formula, to calculate the derivative and the slope of any function at any given point. The only problem is that in some cases the functions are so complicated that using this formula here is too difficult. In this case you need rules in order to do that. But the rules are at the end also derived from this differential quotient that we have stated here. Yeah? And this we will maybe do in one of the next videos. But in this video I would like to give an example which shows how you can calculate the slope of a function really by only using this formula here. And yeah, this we can do. As I said, we will use an example. This should be maybe just a function y of x equal to x squared. This is very simple. Yeah? Many textbooks you find this example, but I would like to calculate now this whole differential quotient with the help of that example. So we have to write here, we can directly use this derivative way to write that, y prime of x1, and then we have to of course insert our limit here, x2 tends to x1, and then we have to insert here this value into this function here, y of x2, yeah, and this gives then x2 x2 square, and the same we have to do here, minus x1 square divided by x2 minus x1. Unfortunately, we have to get rid of this denominator, otherwise we cannot calculate anything. And here in this fraction, how we have written it down here, we cannot do anything. We cannot cancel out anything. So what we have to use is a trick. So maybe you know the third binomial formula, which is given as a plus b times a minus b times is equal to a square minus b square. And when you take a look here at this is exactly what is written here in the numerator. So this is also the trick. It's always you always have to do some mathematical, or you always have to use some mathematical algebraic trick in order to find out how to get rid of this denominator. And in this case, we can do this in the way by rewriting this numerator here with the help of this third binomial formula. So what it gets then at the end is y prime of the derivative of y with respect to x at the position x1 equal limit x2 tends to x1, and then we can write here x2 minus x1 times x2 plus x1, simply the left side here, divided by x2 minus x1. And now you can see immediately what happens. So we have here our denominator looks exactly like that one here, x2 minus x1. So this cancels out. So what remains is also very simple. It's our limit x2 tends to x1, and this will be x2 plus x1. Simple. So now we can easily calculate this. If x2 shifts closer and closer to x1, then this gets just 2 times x1. So maybe we can start on a new page. So our derivative y prime of x at the position x1 would be limit of x2 tends to x1 of x1 plus x2, and this gives 2 times x1, as I said before. So now we know for a parabola at any position x1, the slope that we get is 2 times the value x1. So maybe we can also draw this graphically. So we have here just our coordinate system again and our parabola. So now we can define here a point at the position x1, which can be, for example, 5. And here our function value y of x1 is in this case x square, which means 25. And the slope here, y prime of x at the position x1, would be then 2 times 5, which would be 10. And then you can use this slope to really draw a tangent through this value or to this point, and then this is actually done. So now with the help of this formula, which we have derived here, you are able to calculate the slope at any given position of a parabola. And if you use the definition of the differential quotient, you can calculate the slope of any function at any given point. And now, as I said before, this way of how writing down the differential quotient is normally the one which you learn in school or throughout your studies, but there is another way how to do that, and sometimes it's useful to use that method, and this is called the so-called H method. So what we do, it's very simple. We just define a value h, which could mean help, maybe something like that, and define this as the difference of x2 minus x1, which means nothing else than x2 is x1 plus h. And this is now very, very nice because we can then write our y prime of x1 equal the limit. What we have to insert in this limit, this we have to see now in the next step. But first we go back to our formula, and now we replace here x2 with x1 plus h, yeah, and then we can write here y of x1 plus h minus, and then x1, of course there is nothing changed, divided by x2 minus x1, which is h. So this would be then the way how you can write it. And of course in this case h has to go to 0. Yeah? And this is another way how to write down the differential quotient to calculate the slope at the position x1. And again, I would like to do this with the help of an example, which is again y of x equal to x squared. Yeah, because I think this is a very instructive way to do that. So what we can do now in the next step is use this formula again and insert everything. So we calculate y prime of x1, and as I said, this should be h tending to 0, and then we have to insert here x1 plus h squared minus x1 squared divided by h. Okay, and yeah, then again, limit h tend to 0. We can use the second binomial formula to write here now x1 squared plus 2x1h plus x1 squared minus x1 squared. This should be of course not this should be of course h squared. Yeah? And here we can write down now just simply h. And now you see some things cancel out. This one goes away. Yeah, x1 square minus x1 square. This one goes away. So at the end, what remains is 2x1 h. This h cancels out, and this h also cancels out with this square here. Yeah. So at the end, what remains is limit h tending to 0, 2x1 plus h. Yeah, and this is now very simple. You can see if h goes to 0, then what remains is of course only 2x1. And as you see, this is the same result. What comes out here is the same result of what we have obtained previously with these other method that we have used in the beginning, the more intuitive version. But of course, because we have only done some mathematical changes, at the end the result has to be the same. Yeah, so you can use both methods. Sometimes one is easier, sometimes the other is easier, and especially when we want to derive later some calculus rules, differential calculus rules, then in some cases it's easier to use this h method to do that. Yeah. Okay, but for the time being I want to stop here. I hope that this was somehow instructive, that you learned now a little bit better what differential calculus is, what you can do with this, and in which case it gives you benefits. And yeah, if you like the video, then as usual, please hit the like button. Please write anything into the comment section if you have questions regarding that, or if you want to see more related to this topic. Otherwise, please subscribe my channel if you have not done so far, and hopefully see you soon for a new video.